Hey class. So we all narrowly escaped a wintry death last week, and it's kind of disrupted basically everything we've been doing for the semester. Um, so there are essentially two choices. We can push back, everything, but it's going to cause all of these scheduling conflicts, or we can work through it. Right? Okay, so I could already, I could feel your shudder of resistance from here. So here's what we'll do. I'll give you the solutions, and it's up to you to get it to our noble grader. So uh, yeah, I feel like that is the compassionate response. So the exam is still on for Thursday, and you'll be spotted quite a few points in this class. You kind of I wouldn't say you have to go out of your way to do really poorly, but there's opportunity to do really well in this class. But in particular, I want to make sure that while you're incentivized to do so, that um, you you look over these problems, you still work through them, that we're not going over any less material, and that I don't necessarily lower the standard for the work you turn in. But yeah, we'll get through this one together, and then everything else will proceed as scheduled, right? So, boo, the exam is still on for Thursday. Yay! I'm literally going to show you the solutions. Limit your scathing reviews, or wait until the end of the semester to give me your scathing review on my approach to this. Okay. Uh, okay, so for homework 2, which is still due Thursday, we go through the problems. And so now, instead of confirming these proposed solutions, which were handed to us, we're going to find our own solutions. And so the pattern for each of these, especially these the homogeneous ones, we went over the particular ones the last time we had a lecture, is to find the characteristic polynomial, and then solve for the roots of that, and then use a system of equations where we plug in n equals 0 and n equals 1, and then we have these known solutions, these known values. Then we solve it as a system of equations, right? Okay, I know that this is still, systems of equations is a fairly advanced topic as well. So, we'll just hang in there, right? But the problems that you'll be given, you're essentially guaranteed that you have enough solutions to properly solve it. So it's not oversolved and it's not undersolved. Okay, so the characteristic polynomial, remember that we do r to the n minus 1, r to the n minus 2, and then we divide everything by r to the n minus 2. Or you can just recognize the pattern that it's always going to be r squared, and then whenever you move this stuff to the left-hand side, this will become a negative, so that's negative 6r, and then this will become a positive, and so that's plus 8. So then your polynomial is a quadratic, right? And then you can use the quadratic formula to solve for this, or you can use the fact that 8 has to be the product of the two roots, right? So then it's either going to be two positives or two negatives, but since the middle term is a negative, and since I'm essentially guaranteeing you that you'll get integer roots every time, you can you can take a shot at just factoring it out. And so this is what it factors into. So you have a root. The first root is at 4, and the second root is at 2. Okay, so now we have the roots, and we have these initial conditions, and from homework, from the notes, from the lectures, from the textbook, solutions will have this form, right? So future terms will be a linear combination of a constant and a root to the nth power, right? So the first root is going to have some constant associated with it. The second root will have another constant associated to it. How do we find these constants, alpha 1 and alpha 2? We solve a system of equations. So we know that if we plug in n equals 0, right, up here, right, 0 down here turns into a 0 up here, and we know our roots, r1 and r2, that we can get some information. So we know that when R1 and R2 are raised to the 0th power, well, anything raised to the 0th power is going to be 1, right? Including, by explicit definition, not by any kind of intuition, 0 to the 0, right? So it doesn't matter what the roots are. When we raise it to the 0th power, we get a 1. So we have that alpha 1 and alpha plus alpha 2 is equal to 4. Okay, well, that's not enough information to go on fully, but we have the additional equation that when we plug in n equals 1, right? N equals 1, n equals 1, turns into n equals 1 and n equals 1 over here. We know that a1 is equal to 10, so then we have this additional equation. Okay, so from the first equation, we have that alpha 2 is equal to 4 minus alpha 1. And then when we plug that into the second equation, right, those will make the algebraic substitution for R1 equals 4 and R2 equals 2. And then we make the algebraic substitution for alpha 2. Alpha 2 is equal to 4 minus alpha 1. Then we have only one unknown. We have alpha 1, right? And we know that A1 is equal to 10 because that was one of the initial conditions. So then we just simplify it to where all that remains is alpha 1, right? So then we simplify this junk and we get 2 alpha 1 is equal to, or 2 alpha 1 plus 8 is equal to 10. So then alpha 1 is equal to 1. Well, once we know alpha 1, we have this other equation where alpha 2 is fully determined by 4 minus alpha 1. Okay, simple enough. So if alpha 1 is 1, then 4 minus 1 is 3. So alpha 2 is 3. And then we have, previously, we were given this formula for the closed form solutions to these. Right? So we now know alpha 1, we now know R1, we now know alpha 2, and we know R2. So plugging it into that formula, we get this, but we simplify it a little. We don't need to leave the 1 there. Right? So then a sub n, the nth term in our sequence, is determined by the closed form function 4 to the n plus 3 times 2 to the n. Okay. I feel confident you guys are going to do really well on that homework, right? Okay. So the second problem. Similar deal, right? So now we have another degree 2 recurrence relation. It attempts to trick us by the fact that there is no n minus 1 here, but the polynomial is determined by the furthest term that we reach back for in our recurrence relation. So we're reaching back 2 terms, so then we're going to have another quadratic. R squared minus 1 is our characteristic polynomial, and that has roots at plus 1 and minus 1. Plus 1 and minus 1. Okay, so again, we're going to have something of this form, right? It's our closed form formula for a second degree polynomial with unique roots, distinct roots. Okay. So then again, we solve the system of equations. So when n equals 0, we get to get rid of the roots entirely, and we end up with a1 plus, or alpha 1 plus alpha 2 equals 5, right? So that comes from here. Then the second initial value is going to give us our second equation, right? And if we were reaching back 5 terms, we would need 5 initial values and so forth, right? So that we don't have an undersolved or oversolved system. Right? So then plugging in 1 here, we get this second equation, right? So just like before, right, we have, well, R1 to the 0 is 1, R2 to the 0 is 1. So we get alpha 1 plus alpha 2 equals 5. A0 equals 5, right? And then move A1 or alpha 1 to the right hand side, and we have alpha 2 is equal to 5 minus A1. And then we use the second equation to solve for alpha 1. So then alpha 1 times our first root to the first power plus alpha 2 times our second root to the first power is equal to negative 1, which was our second initial condition. Right? So then alpha 1 times our first root plus 5, or then substituting alpha 2 as 5 minus alpha 1, so algebraic substitution, for alpha 2, okay, times our r2 to the first power is equal to -1 still, right? And then solving for alpha 1, we get alpha 1 equals 3. And then we go back to that previous equation. Alpha 2 equals 5 minus alpha 1. Well, now we know this, so we know alpha 2 is equal to 2. And then now we've solved for alpha 1, alpha 2, r1, and r2. So we plug those values in, we remove any redundancy. 1 to the n is always going to be 1. So now we have that a sub n is equal to 3 times -1 to the n plus 2. Right, so that's how we determine in a closed form our nth term in our sequence. Okay, so problem number 3. So now we have a third order polynomial, or a third order recurrence relation, or a degree 3 recurrence relation, however you want to say it. So we need 3 initial values, okay, and we're going to have a cubic equation. And so this works out that we have a repeated root. So r plus 1 cubed gives us this polynomial. Right? So our repeated root is r1 equals -1, and it has multiplicity m equals 3. Okay, so then the other formula that we were given when we had multiplicity was that the first one is free. Each subsequent one is going to cost you a factor of n, so n and then n squared, right? And then the coefficients are solved for the same as before. So now we use our 3 initial values to create a system of equations involving 3 equalities. Right? So n equals 0. We plug in n equals 0, so this becomes 1. This goes away because of the 0, and then this goes away because of 0 squared. Right? And then our second equation, when n equals 1, we plug in 1 over here, okay, and then we get this. And then when n equals 2, plug it in, and we get 15. Right? So those are determined from the initial values, and then we can make our substitutions using the roots that we know of. In this case, just the one distinct root. Okay, so solving for that first equation, well, these just go away and this becomes 1. So we have, without any work, that alpha 1 equals 5. So let's jump to the second equation when n equals 1. Right, so then it's of this form. Okay, my categories. Okay, so it's of this form, and it's equal to -9. So then 5, and then plug in our distinct root, raise it to the 1, and then we end up with this equation, right? So -5 minus alpha 2 minus alpha 3 equals -9, and so we can put it in terms of alpha 3 in terms of alpha 2, right? So 4 minus alpha 2. Now we go to our third equation, okay, and we know what alpha 1 is, we know what each of the roots are, and we have alpha 3 in terms of alpha 2. So we make our algebraic substitutions, right? Alpha 1 is 5, alpha 2 is still unknown, but we'll solve for it. Alpha 3 is defined in terms of alpha 2, and then we simplify, and we end up with alpha 2 equals 3. Okay, well, we know alpha 2, and we have alpha 3 in terms of that, so then alpha 3 is equal to 1. Okay, so now we know all the roots, we know each of the constants, and so we can simplify it into a closed form function of n. So 5 times -1 to the n plus 3 times n times -1 to the n plus n squared times -1 to the n. Okay, great. Alright, so this problem, which I gave you absolutely no context, but which is pretty simple. I wanted you to recall from your elementary school days that we can write any number, essentially, as a polynomial. The base 16 expansion, we just plug in b equals 16, right, into this polynomial. And we get the base 16 expansion, where the coefficients are between 0 inclusive and less than 16. Right? So the base 10 expansion, right, we would have, let's say, the millions coefficient here and the hundreds, thousands coefficient here. And it would be 10 to, for a million, 10 to the 6, then 10 to the 5, and 10 to the 4, and so forth. Right? So that we're writing that number in terms of a polynomial. So I just wanted you to consider that that is a method of counting. And so we can view really any number in terms of some polynomial representation where we plug in some base value, whatever base we want, and we get the polynomial for it. Okay, that problem turns out to be not so difficult. Okay, so now we have this limit, and we want to show that 3 to the n plus some constant is bounded by 4 to the n. And the way we do that is we use the ratio, right? The ratio test. And so if the limit of g of n over f of n as n goes to infinity is equal to 0, then f of n drives this ratio to 0. Essentially, it bounds g of n from above. Okay, so put it in limit form, make our substitutions. So this is g of n, right? This is f of n, okay? And then we separate it, right? Taking advantage of the fact that we can write this as two fractions with a common denominator. So we have 3 to the n over 4 to the n, and then we have a constant over 4 to the n. Well, as n goes to infinity, regardless of the constant, 4 to the n is going to outgrow it. I mean, even log of n would drive this to 0, right? And then this one simplifies to 3/4 to the n. But this is a constant raised to the nth power, so that will also go to 0. So then we've shown, using the limit test, that this ratio goes to 0, and which proves for us that this function outgrows this function. It bounds it above. Okay. So now we have this problem that is moderately difficult, I'll give you, right? The trick here is to realize that I've made a typo here. And that should actually be in factorial, I believe. I think I made the correction on the assignment, but I might have left it incorrect here. Hold on. Oh, yeah. Okay. Okay. No, that's correct. Okay. So, the log of n factorial is actually a summation. So, it's the log base 2, and you get to choose which log you want to use here. But we're going to use base 2 for simplicity. You could use e, but it's not a natural number base, and so that's going to cause issues. But we're looking for asymptotic bounds, so one log is as good as another, and since we're in computer science, we'll stick with log base 2. Okay, so n factorial is exactly this, so that's exactly equal to. And then using the property of logs, that multiplication inside of the logarithm is equal to addition of the output of the log, right? So this is just by definition of the logarithm, this is true. So now we can consider each of these terms in our summation individually. Well, the log of 1 is always 0, right? So really, we begin our evaluation with this term because this one is 0, drops off. Right? So we want to break it up into two halves, essentially. So there's the smaller half, which we can ignore or set aside for now, and then there's the larger half. These terms beginning with log n minus 1, and so forth to log n over 2 plus 1. So each one of these terms, so half of the terms, n over 2 of the terms, is term by term, right? This is bigger than this. This is bigger than this, right? So each one of these is bigger than the log of n over 2, right? Because inside of the logarithm, where each one of these values is strictly positive, is bigger than n over 2, right? Even the smallest one is bigger than that. So then we can say that this sum is bigger than this sum, right? And so, well, we know how many terms are in that second one, right? Okay, so we go back and we deal with the half that we set aside. So the smaller half, each one of these is greater than or equal to 0. In fact, we could use the strictly greater than here, because this last one is 0, right? But everything else is going to be greater than 0. But we use greater than or equal to treat for the case that n equals 1, right? Okay. So now we substitute back into our original expansion, right? So we rewrite factorial, or this log base 2 of n factorial, as a sum of logs of these inner factors, right? And then we break it up, and we get rid of the smaller half. We just say that this, whatever this is, we don't know exactly what it is, but whatever it is, it's greater than if we took the second half and we just turned it into a 0. And then this is strictly greater than n over 2 times the log of n over 2, right? And that comes from over here. There's n over 2 terms, and each one of them, each one of these n over 2 terms is bigger than the log of n over 2. So then their sum is going to be bigger than that, right? And so we can make this further simplification and say that this, once we have a lower bound, is exactly equal to this, right? So division inside is equal to subtraction of the output, right? So n over 2 times the log base 2 of n minus 1. So in big O notation, you tend to get rid of these constant, either addition or whatever, like you're dealing with asymptotic behavior. So we get rid of the 1/2, the coefficient there, and really we just look at wherever n is. So then we have that this is bounded below by something that behaves like this, right? N times a coefficient times the log of n, minus some constant value, right? So n log n bounds this from below. Okay, so that's the homework. Let's take a look at the exam. Hold on, let me get my cat out of here. Okay. So now, let's walk through it. Okay, so the first part is recurrence relations and proofs by induction. So we're given this problem, which is a fairly famous problem, and so we're adding the first in natural numbers, right? So there is a closed form solution. There's a couple of ways you can arrive at it. You can use the formula that we have been studying on the most recent homework and lectures, or you can solve it for it by using partial sums. So you take the first 10 numbers or whatever and you write them 1 plus 2 and so on up to 10, and you say this is equal to some value s of n. Here, let me draw it out for you. Okay. we say that S of n is equal to this. So we don't know exactly what it is, but we know that you're writing it out like this. It's just a sum of the first n numbers. Whenever you're adding values to a finite number of values, it doesn't matter the order that you write them. So you can write it in the other direction as well. Walking backwards, it's still the same value. Okay, so forward or backwards, it's the same sum. So this plus this, okay, is 2 times S sub n, whatever S sub n is. Well, n plus 1 is equal to n plus 1. N minus 1 plus 2 is equal to n plus 1. N minus 2 plus 3 is equal to n plus 1. Well, this first sequence, this first sum, had n terms in it. The second one also had n. It's the same sum. So then, whenever we add them together, we're going to have n terms. Right? But each one of them, whenever we add it to itself, has the value n plus 1. So twice our sum is equal to n times n plus 1. So our sum is equal to n times n plus 1 over 2, or n squared plus n over 2, however you want to write it. We can actually solve for that one without resorting to new methods. Okay. So we're given this formula, and we're given this oddball representation for that sum. So the first thing we need to do whenever we're proving this is to generate the initial conditions. And you'll notice that whenever you're given a function without initial conditions, that the function gets to say what the initial conditions are, and then we'll see whether or not it satisfies the recurrence. So we plug in n equals 0, we solve for it, and we say a0 is equal to that. We're only reaching back one term, so we only need one initial condition, one initial value. So then now, by induction, proving by induction, we test the base case. So when n equals 1 in the recurrence relation, right, we have 1 plus the previous term, right, a0, and so a1 has the value 1. Our function, when we plug in n equals 1, generates the value 1 times 1 plus 1, so 2 in the numerator and then 2 in the denominator. So we get 1. So our function agrees with the recurrence relation at least once whenever n equals 1. So now we say, okay, let's assume that it holds for some arbitrary number. Right? It might be 1, k might be 1, k might be some number bigger than 1, but it held up until k. So we say, okay, well, if you made it that far, then you can get to k plus 1. Let me show you. So we stitch together the recurrence and the function representation. Right? So when n equals k plus 1, by recurrence relation, we have this form. Right? And then the inductive hypothesis says, well, you made it all the way to k, so we're going to see if you can make it to k plus 1, if the recurrence is the same thing as the function at k plus 1, if you made it to k. Okay? We make this substitution because we were given that we made it to k. Okay? And now we create a common denominator. We multiply this out into a polynomial. we add the numerators with the common denominator together, and then add like terms, so k squared, and then 3k plus 2, and then that factors out into k plus 1 times k plus 2. Well, that is k plus 1 times k plus 1 plus 1, right? So it returns to the form for whenever n is equal to k plus 1, right? So we were able to get into this form. So our function is a solution to the recurrence relation. Some of you might have an easier time using k minus 1 in the inductive hypothesis, so that you have k here, and it in that case you would have k times k plus 1 over 2. Either way. Okay, but the idea is that we've shown that if you have a solution up to some value k, then you always have one more solution. And because the natural numbers have this countability, you're essentially walking your solution forward so that it holds for any natural number if you can make it to a sub k. And so that is what we aim to do whenever we solve a problem using, or whenever we prove a solution using induction. Okay. So now let's do it again. So we're given this other recurrence relation. And so we have this closed form solution, and then we have this summation, a sub n equals 2 to the n plus a sub n minus 1. So generate the initial conditions. Again, we weren't provided them, and so but it's fine because it would have had to agree anyway, right? So the function gets to dictate the initial conditions. So let's choose 0 because that's simple enough. So 2 to the 0 plus 1 is 1. Is 2, right? It's 2 to the 1. So 2 minus 1 is 1. So our value a0 is equal to 1. So now we test the base case. So by recurrence standards, a sub 1 is equal to 2 to the 1 plus the previous term. So that's 2 plus 1 is equal to 3. Our closed form solution says when n equals 1, we get 2 squared minus 1, which is also 3. So it agreed once. Now we say, okay, by the inductive hypothesis, if you get it to agree up to some natural number k, then such that it holds this form, then we can always get to the next natural number. Okay, so we start with the recurrence relation. We make our algebraic substitution. So we know, and by the base case we provided, that this held once, right? And so it held up to some value k. So now we make our algebraic substitution, right? And then we do some cajoling. Well, this is the same as this, so whenever we add them together, it's 2 times this, right? Because we have 2 copies of them. The minus 1, nothing happens there. Well, 2 times this is 2. Well, we pull that in, they have a common base, right? So we add the exponents together. Over here it's a 1, it's a silent 1, and over here it's a k plus 1. So it's 2 to the k plus 1 plus 1 minus 1, right? Well, this is exactly the form of our function f of k plus 1. So it is a solution to the recurrence relation, right? So we've stitched together the recurrence relation and the closed form solution using the inductive hypothesis. Okay, so induction's beautiful once you got it, but I understand that it can be a difficult concept to come by. Okay, so now next one, for n in the natural numbers, f of n, we have our function which provides this form, 3 times 2 to the n minus 3, and we have our recurrence relation, a sub n equals 3 times a sub n minus 1 minus 2 times a sub n minus 2. Okay, so again, the function gets to generate the initial conditions. We're going to need 2 of them, right, because it's a degree 2 recurrence relation. Right. Okay, so when n equals 0, our function gives us something of this form. Right? Plugging in n equals 0, we get a0 equals 0. Plugging in n equals 1, we get a1 equals 3. Okay, so now we test the base case. The recurrence relation says that a sub 2, given these initial conditions, these initial values, is going to equal 9, and our function says that when n equals 2, that we should also expect that to equal 9. Okay, so inductive hypothesis says that it holds for 2 steps in a row, right? Given that it held for 2 natural indices, k and k minus 1, in a row, that we would have this substitution available to us. So we begin with the recurrence definition for k plus 1. Right? Then we make our algebraic substitution, which is the inductive step. Right? So we substitute the inductive hypothesis values, right, here and here. And then we simplify. Okay. And then we eventually cajole it into something of the form which matches our function's representation for k plus 1. Right? So that is also a solution. Okay, so now advanced counting. Okay, yeah, I like this problem. Find a recurrence relation. So now you get to determine the recurrence relation. And give the initial conditions for the number of decimal strings of length n that have an even number of 0 digits. Okay, so the wording is perhaps a little oversimplified. So we're not looking for proper decimals. We're looking for digitized values, right? Base 10 strings with an even number of zeros. So note that we can have leading zeros in this case. Okay, so when the string has length n, there are 10 to the n distinct strings, right? So if you allow for leading zeros, then it's composed of values 0 through 9, comprising n distinct digits, or n digits, and there are 10 to the n distinct strings. Right? Okay. So then, when n equals 1, we have our initial value, a1. There are 9 strings with an even number of 0 digits, right, where 0 is counted within the string an even number of times. So there's the single case where our length 1 string is just a 0. And then there are 9 other cases where we don't have 0 at all. And when there are 0 zeros, it's an even number, right? So now we have this this secondary set, this helper sequence, which will count the number of strings that will eventually that we can turn into strings satisfying our condition. And so it's the b sub 1 is equal to 1. So the number of strings with an odd length, right? So that'll be our secondary sequence. So there's the ones that satisfy the condition and the ones that we can make to satisfy it in one additional step. So strings of length k plus 1 with this property can be constructed from the a sub k strings that satisfy the property by appending any digit other than 0. So 0 through 9, right? If we tack it on to something that already satisfies the condition, then we've generated a new string of length n. Otherwise, if we have one that can be made to satisfy it, then we can tack on an additional 0 to these strings, the values in this sequence, and the ones that were previously a solution, and we tacked on some 1 through 9 character, and then the ones that were not a solution but had the appropriate length. Now we tack on another 0 to those, and it now has an even number of zeros. Right? Okay, so the k plus 1 term is going to be greater than 9 times the previous term. Like we always know that'll be the case, right? Because there's 9 ways to create a new string from previous solutions using just the set that solved the previous step, and then there's always going to be some additional number of near-miss solutions. Okay, so then there's an additional b sub k ways to construct the string. Essentially, you add another 0, and it goes from an odd number to an even number. So then now we need to solve for b sub k. So how do we construct these strings of length k that have an odd number so we can keep track and toggle them in at each step as is appropriate, right? So to properly account for a sub k, we need our helper sequence, and we need to track it every step along the way for strings of length k. So it's a complement to a sub k. So we know that there's 10 to the k solutions, and we know that it's essentially the ones that aren't solutions, right? That don't satisfy our property. So 10 to the k distinct strings of length k minus the set of ones which are have an even number of zeros. That is our set of strings of length k that have an odd number of zeros. Right? So these are complementary to one another. Okay. So then a sub k plus 1 is equal to 9 times a sub k plus b sub k. So the set that previously had length 0, and then you stuck on some digit 1 through 9. So there's 9 ways to do that for every string in the previous set. And then the set that had an odd length. And there's only one way to make them satisfy the evenness condition, and that's to tack on a 0. And this number is given by this, 10 to the k minus a sub k. Well, now we have a sub k here and here. We can just combine those. 9 minus 1 a sub k. So we have 8 a sub k plus 10 to the k. Okay, so that's the solution. Great. So now, next problem. Given the characteristic polynomial r minus r1 times r minus r2 is equal to 0, find the associated recurrence relation. Right? So hint, this problem does not require identifying the initial conditions. So the idea is that the characteristic polynomial, I mean, it's a two-way street, really. Like, you could generate these recurrence relations from closed form solutions and from polynomials. There's, you can backtrack your way to a recurrence relation given a function, right? And so this is just an intermediate step. So we're not starting all the way from a function, from a closed form solution. We're starting from just the polynomial. And so you expand it, right? You multiply it out, and you get r squared minus r1 plus r2 times r plus r1 times r2. Right? So then move it over. So you're going in the other direction of what we've done up until now. So r squared is equal to r1 plus r2. Right? This moved to the right-hand side times r minus, so this moved to the right-hand side, r1 times r2. So then the associated recurrence relation, right, from here is a sub n is equal to this coefficient, right, times a sub n minus 1 minus this coefficient times a sub n minus 2. So it's just a different way to look at the problem and to show that there's this intimate relationship, this one-to-one relationship between these the characteristic polynomial and the recurrence relations. And then if it went even further, then there's this relationship between these functions, these exponential functions, based on their coefficients, and their and a recurrence relation with initial conditions. Right? But we haven't gone all the way to that step. Okay, so now find the closed form solution for the recurrence relation a sub n is equal to 9 times a sub n minus 2. Right? So it's a degree 2 problem. We're given 2 initial conditions. So we convert it into the characteristic polynomial, find that there are two distinct roots, and just like with the homeworks, now we have the form for our solution, and we solve for alpha 1 and alpha 2. Okay, and we know that when n is equal to 0, the function has a value of -3. When n equals 1, it has a value of 6. So now we use that and we solve for alpha 1 and alpha 2. So alpha 2 in terms of alpha 1. And then we make our substitution here, right? Alpha 2 here. And we solve for alpha 1, and we see that alpha 1 is equal to -1/2. Alpha 2 is equal to -3 minus alpha 1. So then it's -5/2. Okay, so then our closed form solution has this form, right? So you can put it like this, or you can combine the fact that they are both divided by 2. I think this is actually cleaner, but if you want, this is also acceptable. Okay, so that's our closed form solution. Okay, so now relations. We haven't really discussed this all that much, but hey, let's go over it now while we're here. Right? So list the following triples from the table which satisfy the selection condition. Right? So this is structured query language syntax, so it's SQL syntax, SQL. And so you're given a set, or a table, which defines a set of records, right? And you restrict the set to satisfy a certain condition. Right? In this case, the record's value for this field satisfies chemistry, the string chemistry. And then you select out, so you project down to some smaller tuple, right? So initially we have 4 fields in each record, but we only want 3 of those fields returned from our query. Right? So student ID, student name, and GPA. In particular, because we already know what the major is. The major is chemistry. Right? So given this table and this query, what are the triples, the tuples with 3 fields, that satisfy this query? So we're selecting the records equal to chemistry, with a major equal to chemistry. So then the triples, note the parens, the parentheses. So student ID, right, for these records that satisfy it. Student ID, the string name, and then their GPA, right? And so we would be given 2 tuples which satisfy that. Right? And so our solution set would have 2 results in the result set, each one of them composed of the number of fields that we selected for. Right? Okay. So now draw the directed graph represented by the following ordered pairs. So directed graphs have arrows. And so ordered pairs have a source and then a destination, right? So we have 4 vertices that are represented here, right? 1, 2, 3, and 4. Right? And then they are related. We have this relation set by these source and destination pairings. So 1 to 2, so we have an arrow going from here to here. 1 to 3, so we have an arrow going from here to here. 2 to 3, so there's an arrow from 2 to 3, 2 to 4, right? 3 to 4, and then 4 to 1, 4 to 1. And so you can see the arrow indicates which direction it's going. Okay. And so these are like one-way streets, right? As opposed to two-way streets. A directed graph allows you to have this one-way street representation where you can only go in one direction. Okay. So now we're given another relation, right? So again, source and destination pairings, right? On the set A, right? So we have these are our vertices, 1, 2, 3, 4, and 5 now. We want to find the symmetric closure on our result set. And so symmetric closure and the other closures, they're just where a property is fully satisfied by the relation. So in this case, we have this reflexive, if we have, so one type of closure is the reflexive closure. In that case, we would expect that each of these nodes to have a loop back, essentially. So any computer on a network can also access itself even if it's not connected to the network. So it always has that reflexive nature. So you can always test things deployed on your system without having to actually go out to the network. You have this loop back interface. Right? So that would be reflexive closure. Symmetric closure means that if you have something going in one direction, like from 2 to 4, then you have it going in the other direction, from 4 to 2. If you have it going from 3 to 1, then you would expect from 1 to 3. From 4 to 1, the symmetric ordered pair would be 1 to 4. From 5 to 2, it would be from 2 to 5. And if you were to use an adjacency matrix to write this out, then the symmetric closure would be a symmetric matrix. Right? So if it's not symmetric, then the things that are 0 where its symmetric component is non-zero, you would overwrite the 0 with the non-zero value. Right? So the symmetric closure for this on this set is going to be just the pairings where symmetry is not satisfied, right? So 1, 3, 1, 4, 2, 5, and 4, 2. Right? So that's what we're looking for there. Okay, and then the bonus problem, I give you a link to an online compiler that you can use to attempt it, and I want it written in Go. And so implement merge sort in Go. Well, the notes already have merge sort implemented, so you just have to try it out with a new language. And so go here, make sure that it compiles. And I will provide you with something to get started, but it's not going to compile. As before, I encourage you, rather than copying and pasting it in and getting frustrated, type it out. Start out with whatever they give you in the given language, and then go from there. Okay, so hopefully you all do really well on this exam. Okay, so now let's continue with the lectures as we had originally intended. So we were on, let's see. I feel like we already covered this. Yeah, so we covered the multiplicity. So if S is a root to the characteristic polynomial, then we use this additional value, this factor. Otherwise, the particular solution has this form. Okay, so we're given this, right? And now we're given, so this is the homogeneous part, and now we're given a few different particular examples, and we're going to work through them, one by one, so that we can get a feel for what all this jargon looks like. Okay. So the first thing that we have to do is solve the associated linear homogeneous recurrence relation, and then we see whether or not S in the particular function, right, the non-homogeneous part, if that is also a value in our homogeneous solution, right? Okay, so here we've identified that S equals 3, in this one S also equals 3, in this one S equals 2, and in this one S equals 3. And you can see that it's multiplied by polynomials in each case, right? So both the non-homogeneous part and the particular solution will be that value S to the n times some polynomial, and then possibly times something else. But it's not going to, we wouldn't expect it to be the same polynomial as in the non-homogeneous part. So the closed form solution, we would expect it to be potentially a little bit different. So here the polynomial is just a constant, 1. Here it's the value n. Right? Here it's n squared, and then here it has the look of a quadratic times that exponential. Okay, so we've identified s in each case. Now we go back and we solve the associated linear homogeneous recurrence relation, which is the same for each one. And that's a sub n equals 6 times a sub n minus 1 minus 9 a sub n minus 2. Convert it into the characteristic equation, right? So it's a polynomial. We decide that we don't like r to the n. We like r squared better. Right? So then r squared minus 6r plus 9 equals 0 is our characteristic polynomial. We find that we have a repeated root, r equals 3. Right? So now we go and we find the particular solutions. Okay. Excuse me. Okay, so when the non-homogeneous function is equal to 3 to the n, we have some polynomial which depends on n times s to the n, and then b sub 0, right, is equal to 1. Right? So this is the formula, the form of it that matches what we're testing for. So b is our input polynomial. It's what's given to us, and then p is what we're solving for. So we know that s does have the same roots as one of our polynomials, or sorry, it shares one of our characteristic roots, which has a multiplicity of 2 in our homogeneous part. So then here we know that m will equal 2. So we don't know what p0 is, but we know that it's going to be there, right? Okay. So then whenever f of n is equal to n times 3 to the n, we have a function f of n of this form, right? So our input polynomial has this form, right? N times 3 to the n minus 1, right? So n is b1 is a non-zero, the largest non-zero coefficient. So then as this form, s is equal to 3. It's one of our roots. So then our solution, the particular solution, will have this form, largest non-zero coefficient from over here, right? So we know it's going to be some linear function times n squared times 3 to the n. Okay? So now when the non-homogeneous function has this form, well, n squared is the largest non-zero coefficient, right? So b2, right? So we would expect p2 to be present in our solution. 2 is not one of our roots, so we don't have to multiply by n. Right? So we have this polynomial times 2 to the n. Right? Okay. When our non-homogeneous function is equal to n squared plus 1, all times 3 to the n, then well, n squared, so b2 is our largest non-zero coefficient, right? So then it has this form. S was one of our roots with m equals 2. So then we use this for our particular solution. So m equals 2, so that gets plugged in here. P2 is associated to b2, right? So n squared is present, our largest non-zero coefficient, and then s equals 3, right? So then our particular solution will have this form. Okay, but I don't make you go through and solve for that explicitly. Alright, so now we can discuss divide and conquer algorithms and recurrence relations. So algorithms like binary search and merge sort are prototypical divide and conquer. And so how do we count like the number of steps? So previously, if we just run a loop, if we just executed a loop, it's pretty straightforward. Everything inside of the loop got executed however many times the loop iterated. But now we're diving down, so that we're executing something, but we don't really know. It's more complicated to track how many times that something is being executed. So let's return to a definition. So let a recursive algorithm divide a problem into size n, of size n, into a subproblems. So whenever we're dealing with binary, right, or even merge, a is 2. So each time we break it up, we're breaking it up into 2 pieces. But you can choose some different value. You can choose ternary sets, right? So you're breaking it up into thirds, or you're breaking it up into fourths. So there's a general form for this. But typically, the things that we've looked at, we're dealing with either left or right. So it's going into 2 subproblems. I suppose you might consider 3 problems if you say, well, I'm checking for equality at the current value at the midpoint, and then there's the left and the right. But if it's the midpoint and you have equality, then you're not really invoking the function any additional times, like it terminates, right? So those one-off tests would fall into this G of n, this other stuff that you're running each time you execute this recursively. Okay. So suppose that there's a total of G of n extra operations that are required in the conquer step. So we want to make comparisons. We want to see if it's to the left or to the right. We want to see if the midpoint that we're testing is exactly equal to. So those all get lumped into this G of n, and they're executed each time. But the recurrence is going to determine, for the most part, how weighty our algorithm is. And so, less than, equal to, whether we're going to swap elements in an array, in the case of merge, and so forth. Right? And so then the divide and conquer recurrence relation of this form will require f of n operations to solve a problem of size n, where f of n satisfies the recurrence relation. This, right? Well, we've spent quite a bit of time discussing recurrence relations, so this shouldn't be all that intimidating now, right? So we have this non-homogeneous part, this particular part, and we have this homogeneous part, right, where we do a constant number of repetitions of some previous step of recurrence, right, where we're diving down, or we're breaking it up into n over b parts. Right? Okay, so it's kind of a lot to take in, even as familiar as we are with recurrence. So let's take a look at a couple of examples. Okay, so in binary search, we look for an element within a collection. So we're looking for a single element out of n items, but we're given that the items are sorted previously, right? So we can break it up into 2 halves, right? Or whenever I was discussing the dictionary and we're flipping it, we're opening up the dictionary in half, and we're saying, okay, well, the word we're looking for has a first letter that's to the left of this, or that begins before this, or first letter comes after this midpoint, and so then we continue to break up the pages into half and look in the left or right as appropriate if we don't find the exact page we're looking for. Right? So that's exactly what we're doing with binary search. And so each time we break it up, we count G of n equals 2 operations. So is search item less than the midpoint? Right? So we're sizing up G of n, right, which is this part right here. Right? So we're going to see if we can put A, f of n over b, and G of n into perspective. Right? So G of n has exactly 2 tests. Is search item less than the midpoint? And then is min item less than max item? So if that's not the case, then we terminate our search because we didn't find it. If search item is less than the midpoint, then we check the left half. If it's greater than the midpoint, we check the right half. And there's actually a test for equality in there too, but So that should be 3, not 2, but don't worry about it. Okay, so we could count additional operations such as max item equals midpoint minus 1 and so forth. But the key point is that we perform some constant number of operations, g of n equals k, each time we divide the problem. So here we listed as 2. Again, we could add another one if we wanted to test for equality. We could add another one each time we perform some operation, right? So subtraction is an operation, assignment is an operation, and so forth, right? But whatever, right? It's just in that neighborhood. So long as it's constant, we're not performing loops. If we were performing a loop, then we would have a function which depends on n here, right? Okay. Or k, if you prefer, whatever. Okay, so since we need only visit 1/2 of the divided collection, we only have one subproblem to solve with each recursive step. So we never go back and we check the right half, which is what we're doing with merge sort. Whenever we're merging the stuff, we're performing operations on both the left and the right half. But here, we're only looking into one side. So A, even though we've divided it into 2 subproblems, we're only diving into 1/2 of those subproblems. Okay? So thus, for the number of comparisons, f of n, for our binary search algorithm is equal to this. Well, we have a value for A, we have a value for g of n, and we have a value for B. So then f of n is equal to f of n over 2 plus 2 or plus k, however many individual operations you want to discuss. Okay. So then the merge sort algorithm splits an unsorted list of n items into 2 lists with n over 2 elements when n is even. So they are the size of n over 2 and n over 2. And remember, we continue to divide it until we end up with just these singleton sets, which are fully sorted, right? Because they're the only thing in their array. And so uses fewer than n comparisons to merge the list, though with the while loops at the end of pulling leftover items, we can round this value up to g of n equals n. So then the number of operations used by the merge sort algorithm to sort a list of n elements less than m over n, or m of n, where the function m of n satisfies the divide and conquer recurrence relation, right? So this is merge sort m, right? So m of n is equal to a 2, right? Because we do divide and conquer and visit both halves of the set that we're sorting, times m of n over 2, because we're breaking it up into 2 halves each time we call the function recursively, plus n, where n is our merge operation. So each time we're given n elements, so a left and a right, left plus right equals n, right? So the 2 halves add up to n. Then we perform that many assignments into our array. Like I said, if you have a loop, then you're going to have some function over here that depends on n, some g of n with n. And if you had a loop within a loop, then this would be n squared and so forth, right? So then you have some recursive function that looks like this. Okay, great. So the theorem, I think this is the master theorem. No, the master theorem's next. Okay, well, let's discuss that next time. So we'll come back and we'll discuss the theory. But we now know how to sort of count our recursive functions and put them into something that looks like a recurrence relation. And the next thing that we're going to learn is how to turn that recurrence relation into a big O notation, right? So we can use our recursive functions and our recurrence relations, representing the number of operations in those recursive functions, and get a feel for exactly how bad our code is. Excellent. Okay, so again, hopefully none of you are stressing too much about the exam on Thursday. Your homework is still due on Thursday, right? But it shouldn't be too bad in light of this lecture. Okay, have a great evening, and we will speak again on Thursday.